Hi everyone, and today I'm very privileged to have Marius and Leo to be here to share with us again about symbolic AI. And this time around, they have written a paper. And without further ado, let us take a look at what symbolic AI is and what they have to share.
So thank you, John. Yeah, hi everyone, I'm Marius. Here's Leo. Yeah, we are basically thrilled to present to you now our academic paper also to the framework that we released like a year ago and constantly updated and refined, which includes, different kinds of solvers, and different kinds of like models that are combined in one coherent framework that kind of binds them all, so to say, to try to interchange between different, let's say, foundation models, but also like specific models and different kind of tools and as I said, solvers and other objects, basically. So yeah, without any further ado, I would maybe also a few words from Leo, and then we're gonna start.
Yeah, hi, I'm Leo. I mean, we already know each other, I guess, after so many videos with John. Yeah, we're kind of familiar with each other at this moment in time. Yeah, so I basically am the second author on this paper. We work closely to basically formalize the framework and let's say give it more weight in an academic format, if you want.
Thank you. Okay, so let's start off. Quickly share my screen. You should see everything, right?
Yeah.
Good. So yeah, this was also joined to work with my colleagues Markus Holzleitner, Werner Zellinger, and Sepp Hochreiter, which you're probably very familiar with. And yeah, the full idea of the paper, just to bring this in one picture, if you want, so holistic picture, was to how can we bridge the gap? What we usually observe is like between like machine learning, papers or research questions where we have everything data driven and everything learned versus software engineering where oftentimes we use heuristics or implementation details to close the gap usually where models don't really are proficient at. And how can we like capture all of that and find some framework that can easily basically migrate between these realms. Specifically also we focus on between different foundation models or maybe specialist models where you specifically tuned for a task, and also where you see the contrast to this in the software engineering realm between abstraction versus the actual implementation details. And this whole thing is basically the neurosymbolic AI spectrum that we were talking about also with the GitHub release back 1 year ago. We said a neurosymbolic perspective on large language models, basically. So this is kind of like the just in one picture the main idea. In this paper, what we also did is now we obviously introduce our framework formally and a bit more rigorously, academically, at least speaking. But also we introduce a couple of other things alongside it. So we also introduce basically a quality measure to evaluate, because different computational graphs. So you when you stitch together different, let's say, generative processes and so on, especially with ones that are maybe hard coded or databases, or as you know from RAG or something like that, augment, the question then will arise as you can't stitch quickly something together, but the quality of it, or is it representative for what you actually expected to get as an outcome? And usually with LLMs and so on, as quote unquote central processing units in your computational graph, it's not really deterministic really what you get out. So this is kind of like where we try to introduce our own quality measure that assures and says like how far off are you from what you would have expected, which is basically based on some embeddings, which we call vector embedding for relational trajectory evaluation for cross similarity. So I'll talk about this later on in more detail, but the idea is that we have basically a multi-step generative process, and we have some reference data distribution, if you want. So, and we compute the embeddings and measure the differences between distributions, basically between different generative nodes. So that's in a nutshell explained.
There's a quick question here. So I
Yes.
really like symbolic AI in the sense that it's integrating very well with a lot of different engines like OCR, text to speech, sorry, speech to text, image recognition. You can even do like basically any kind of thing you can put as a pre-processing step. It goes into the symbol part. You can manipulate a symbols, and then after that you can do your post-processing accordingly. So symbolic AI is very flexible. It integrates a lot with different kind of modules, different kinds of APIs. I just want to maybe also on behalf of the viewers just ask a quick question. Like
Please.
frameworks, open source frameworks like LangChain that allows you to use large language models and also do different tasks, run agents to do some question answer and so on. How would symbolic AI compare to frameworks like LangChain?
Yeah, thank you for the question. So LangChain and Symbolic have maybe the same concept of using large language models, but we kind of like differ then at many points where we say like architecture-wise we differ because of the philosophy already from our framework is that we have abstraction built in from start with this symbol expressions and all the, the hierarchies that we derive from these different expressions. So we focus heavily on the mathematical formulation here, how to create these computational compositions basically of different functions, which I think they call chains or so, LangChains. But also not only that, we're not heavily focused also on large language models per se. We always talk about in our framework about neurosymbolic, engines in the background, because you could replace any, theoretically, you could put even like a classical hard-coded, if-else statements in the background if you could interpret obviously your symbols in the front end the way you wanted it. So you could flexibly interchange between different, models or even implementations. And this is just a couple of differentiations. And we focused also from the start when we said we want to have, ways to measure, for instance, the generative paths and so on. And this is what we always claimed since a year, because if you can't measure it, you can't optimize it, you just get some randomness out of some stitched together system. So this is kind of like we went away from just templating towards more optimization. And this is exactly where we heavily also integrate with interfaces from PyTorch and so on. That's what we kind of focus on and try to also tackle the next realm in optimization in the next release. So this is kind of like, in a nutshell, the philosophical differences between our frameworks.
Very nice. So at the core, the way you process things is no longer just as like a large language model output. Everything is given a symbol, and this symbol is the core of the framework. And
Yes.
based on like our previous videos or so, you should already have seen that, like, or if you haven't seen, a symbol is quite flexible. You can match like a tree with a number tree with the word tree, and it will still match. And like all these things can be done like natively, because the outputs of all the engine calls for the symbolic AI framework will get stored into a symbol. And I think the most amazing thing about this symbol is that it can be interpreted using the string function, which is str. You can just ask it to output as a string, and you can see what's in the symbol, like be it like this, a sentence, like some JSON output. Everything can be a symbol. And you can compare symbols together because there's a fuzzy equals inside. I think Leo talked about it last time. So this brings me to my next question. So the framework is called Symbolic AI. Okay, so in traditional symbols, the symbols are kind of fixed. Like, for example, if say a bird has feathers, it just really means feathers. Like, it doesn't mean the bird has something that can fly, It doesn't, it's not as flexible. So, why do you decide to call it symbolic AI? Because the traditional symbolic methods have a connotation that the symbols are fixed, but actually in this framework, the symbols are quite flexible.
Yeah, thanks for the question. So I mean, symbols, we also talk about here when we define basically symbols and expressions, how we got inspired also by Newell and Simon's work basically around the 50s to 70s, 80s around, where they kind of talk about symbols being like physical patterns and being capable of composing complex structures, basically. So this is kind of like how they see it. And this is exactly how we got inspired, where we talk about like anything could be a symbol in our framework. So you could say like, if you define your image being a symbol, that's fine. It could be a symbol. I mean, if the question is if you're, let's say, neurosymbolic engine can then interpret that symbol that easily. So if you would use an LLM, for instance, as a neurosymbolic engine, that's one example, and you throw it the entire array of like a three-dimensional, tensor basically as an image into it, then that's kind of like hard for the LLM to interpret, right? Because that's not how it was trained, optimized. Obviously, you could use another backend. They could use something that has an image to text or so, and then you could get back a different representation, which would be a compressed version of that symbol. So you would have maybe the image on one hand side, but then you would have a, let's say, text representation which just says cat, because that's maybe what's on the image. So that's why we kind of like say one and the other are both two symbols. The question now is, how do you associate them? And that's kind of like, you can think of also a main part of our framework is the association between symbols, right? So when you bridge the gap between modalities, you could say like, look, this is an image, a full array image, but this is just saying cat, because that's basically the main content, like the abstraction within that image, so to say. And both are basically symbolic representations, to be honest, because also image is actually an array of very discrete integer numbers, right? So, but the main idea behind this is to build these associations to operate with the abstract concept space versus not the different arrays and the high dimensional representation of it. So this is kind of like the gist why we call everything symbols, and that kind of inspired us to also say like, actually we name our entire framework, but in the end the aspiration to Newell and Simon's work, symbolic AI, because it's also the kind of inspiring to say that it's the resurgence again from symbolic computation versus all these connectionist models that we experienced the last 20 years, if you want. So it's kind of like refreshing to reground ourselves and say that everything is kind of a symbolic representation, even LLMs, actually. If you think about all the heuristics of how we samples tokens and all that stuff on top of it, you always have some symbolic representation that kind of, grounds it back or has some ad hoc realization of how you would obtain the next token and so on, right? For instance, even although it's a sub-symbolic model basically doing the computation.
Yeah, so it shouldn't be conflated with I mean that there's also like symbolic AI, like our name, and symbolic space AI, which is basically like the entire field of symbolic AI. We just mean symbolic in the way of using symbols. That's the point of the
it's
name.
A name game. It's a name game. Yes,
it's a name game, exactly.
Yeah. But yeah,
I'd like to highlight that this symbol is not the traditional symbol that is unchanging and fixed. This symbol can be interpreted flexibly. And like as I said, the number 3 can equals to the word tree. Which also leads me to the next question I have is that, like, how do you know what is similar? Like, how does the symbolic AI know how to equate things to be similar? Like, I mean, could the similarity change based on the context as well? I mean, is this also incorporated in the framework?
Yes, so that's a good question. So exactly, that's what we use the neurosymbolic engine to evaluate. So obviously, the best neurosymbolic engines nowadays are large language models, specifically very prominent with GPT-4, where we see that they trained on so large text corpora that you can basically now just say, like, if you have two, let's say, representations saying, I don't know, pi, the symbol pi equals 3.1415 whatever, you could equate those two and ask like the question, is this the same concept or is it the same thing, like a fuzzy equals, as you said it earlier, right? So the idea is what we are doing in the framework to get these equalities of abstract concepts is by defining certain operations or operators, where we have it. Sorry, yeah. I mean, this is the function of the composition. It's more technical detail further down, but the main idea is to create, as you see it here, the example.
Yeah, that one.
Exactly, that was I looking for. So you see here, for instance, where you could say we create different kinds of operations that kind of show this similarity, these associations actually, where we say like A is equal to B because of this and this trait maybe, and so on. And we do like a few short examples, as you probably know already from in context learning and so on. And then we say like, actually, when these things are equal, what would be the next expected operation to be equal? And then you usually just ask it, is this and this now equal? And then you get a true or false answer back. So this is how we kind of do this associations between different abstract concepts. And then we have this dedicated operators that kind of bridge these gaps between the different associations. And then we, just let the neurosymbolic engine, in this case, LLM, because they're very proficient in this association evaluations, to give us the results back. Obviously, our framework is very grounded also in formal languages, as you see it here as a paragraph, and also in context learning, therefore. Because to maybe just cut directly to the image, why do we use formal languages? Because if you would just ask in textual form, like, is A and B equal? And then you just keep on asking and so on, you would never get a structured answer back from an LLM. That's kind of the trait and the problem of it. The nice part of an LLM, for instance, is that it understands obviously programming languages and all these concepts of like very structured way of, where comes the if statement, the comma, the whatever, all these details, right, what matter in programming. So this is obviously because it's grounded in formal languages, because there were obviously formal languages defining the structure of the grammar basically, and then defining structure of the programming language itself. So we kind of use this, if you want, so as a what we call situation-specific grammars, which we kind of bridge the gap between grammars and in context learning, if you want. So where we say actually you could see the prompt as you know it usually as a domain-specific language, where you have your, you write one operation which describes at the beginning what the task description is, right, as you usually know it from in context learning. And then you have a very structured way of, giving the answers, or also building up the associations, where you say, maybe say like, we have some examples in the appendix, but just to give you the gist, is like saying like we start with quotes maybe, then we give it the first symbol or object, end quotes, colon, for instance, then we start another quotes, then there's the second symbol, then implication sign, and so on, right? And this is a very structured format how we want to get the replies back, and we do this for a few shots, for instance. This is how that's what we call the domain-specific language prompt, if you want so. And then we always expect also in that format to, when we query it in the end, right, with the last question, so to say, then we expect to get this reply in the same format back. So to resolve this thing here, what you see is basically you would have a symbol AC, you would have an operator, in this case, the left shift operator, you would have a second symbol B. This whole thing is an expression, a mathematical expression, if you want so. And now what happens with this like formulation, it would get basically resolved in a domain-specific language prompt, where you would have the task description at the top, some formatted examples, and then the implication sign for the last operation. And basically then you would throw this to a neurosymbolic engine, which is mainly a LLM at this time being. And then you basically get your next symbol out of it, which is then the most logical interpretation of it, being ABC concatenated, like B is shifted into ABC in order format, in alphanumerical order.
All right.
Yeah, so this is the main idea.
So I'd like to just rephrase some of the things you said. So maybe you can correct me if I say it wrongly.
Please.
So in this case, it looks like the expression is like an instruction. So in this case, you want to left shift and put in the symbol B. So it's like, it could also be something like a worded instruction, right? Like put B in the middle of A and C. That can be an expression, right? Expression is basically an instruction that you want the program to execute. But which
Exactly.
we don't know yet, but it's just an instruction. Different programs can interpret the instruction differently. In this case, your DSL prompt, or your domain-specific language prompt, is basically constructing a program to interpret this expression. So
yes,
this DSL prompt could give some examples like AC, left shift B, then the answer is ABC. Then it could also be like AD left shift B, the answer is ABD. So you could give some examples, okay? Or it could be a fully deterministic program, right? It could also be like a rule-based system, if-else kind of system that
Of course,
interprets the
you could.
abstraction directly. So the DSL
Exactly.
prompt here could be both deterministic and fixed like traditional programming, or it could be very flexible like the large language models, or it could be both. Right? I mean, I
Yes.
don't count that you do. I mean, in this case, DSL prompt here sounds like it's going to a language model already, right? Because
Yes,
it's a prompt.
exactly.
Yeah, but I
Yes.
mean, the symbolic AI architecture also allows you to interface directly with a traditional classical function that doesn't need LMs.
Yes, exactly. Like Wolfram Alpha, for instance, you could use a solver in the backend where you could you just have to rephrase your maybe full text representation into some symbolic mathematical formulation, and then you could just throw it at Wolfram Alpha. They will resolve, do the computation, do the maybe proof or whatever. You query it, and then you come back with the result, and can use that again further on in the framework. So that's kind of main idea. And you said also a very important thing about like this kind of what you said, like it depends a bit on the the function kind of is dependent a bit on the data indirectly. So this is kind of this what we call this polymorphic trait of operations. So where we would say you have the operation description, but it actually even depends what you put in there as a data, right, representation, because different abstractions have different kinds of meanings. How you would like the very famous king minus man plus woman is equals queen example with the embeddings. You can emulate that thing also in a symbolic form in our framework, where it also creates associations that it's very close to this abstract concept manipulation. But depending if you put now king, or if you put prince minus man plus woman is then a princess, right, and so on. So you might have then all these polymorphic behaviors depending on the data, because there's in this case a semantic meaning or a semantic operation happening, because the semantics obviously in this case are the because you're subtracting or adding strings if you think about it. So what would it mean? But since you know the context already, which is kind of polymorphic behavior on the abstract object, then you basically can abstract and say, okay, maybe semantically, like a human would also say, maybe he means if you take out sex basically, then and you add another representation, that this is resolving into this new object or a concept that we're talking about, right? So this is kind of like the main idea behind this polymorphic functions that we kind of build. And yeah, and to maybe sum it up, so what we talk about here or these polymorphic functions, why this works is because they're what we call they're like domain invariant associations. What happened here? So think of it very, very specific use case. Think of it, you have on one hand side your Java programming language, and on the other hand side you have Python, for instance. So they're very distinct domains, right? So you couldn't just take one and put it in the other and compile it or let it work. So but the idea is that there's a common thing that grounds both of them, the logic behind it, right? You might have some logic representation, and then you have the syntax, how you realize it, because this is dependent on the trait of the language, right? So, but you want to just abstract on the logical concept space, and you want to create this bridge from one language to the other, and port over the logic basically, and just realize it in the new concept, right? So what you would do is obviously write maybe an instruction that says like, look, both are programming languages, but you want maybe some keywords, you give even some examples to help it understand the concepts that are the same. And then you basically say, I want now the logic from Java ported over to Python, that I can use this in Python, meaning also that all the libraries and dependencies are resolved correctly, right? So these are kind of like your DSL would describe all the tasks, or describe the entire like translation process and so on. And now you basically are kind of bridging or creating an association, a domain invariant association between both languages, because you care only about the logical concept space that you kind of port from one to the other. And yeah, this is what we believe is a very powerful tool. What was missing in our tool set of all fully learnable systems or just symbolic systems. This is kind of like a concept space that we can use with very fast abstractions, and then do these operations in this concept space then, and port it over to another space, right? Which is very, very flexible in our tool set nowadays.
So actually in my YouTube videos as well, I've been talking about multiple abstraction spaces. Like I believe in order to solve a problem, you not just need to do one abstraction space, you need to do like multiple and pick the best one. Like for example, images could be pixel space, object space, and so on.
Mhm.
So how I treat this is something like a mapper. It maps from like some input into a space that is semantically meaningful for your problem. Is that more or less what you were
Exactly.
describing?
Exactly. So that's the domain invariance, if you want. So right, you not that language Java is equal to Python, but the logic behind it is invariant. Like you kind of, by just prompting it in the correct way, you get this, this latent features, or you get basically these activations that in this activation landscape, if you think about it this way, the logic is kind of invariant because it's the same logic. Obviously, the syntax then collapses to a fixed point, which is realized in their distinct traits of writing down the logic in the programming language. So that's kind of like how we see it, at least.
So where is this? Is this in the DSL prompt? This association?
Exactly. These associations are happening, most of them obviously in the DSL prompt. The description kind of grounds the model in this direction. Obviously, this is connected to LLMs, obviously.
So this one is something like the zero shot prompting, which is that purple text which just describes what you can do. And the few shot prompting is those things that are below the purple
For
text.
instance, yes.
Prompt that tells you like example 1 do this, example 2 do this, example 3.
Exactly.
By combining both the zero shot description and the few shot prompting, it makes it
Yes.
very versatile and is able to interpret even the expressions that it has not seen before in the few shot. It can sort of generalize to
Exactly.
other examples.
Kind
I
of,
mean, the idea here would be to, like, we as human beings, right? We just look at a few examples and you just easily understand. So it would be, I mean, what we call in this specific context, few shot examples. It's very similar, like you do like let's say it's like the examples that you would see in the ARC challenge, right? When you see like at least 3 of them, and then you're asked basically Raven test, Raven/IQ test, right? You are expecting the agent or the large language model, or more general, the neurosymbolic engine, to complete the pattern, if you want, right? Because ultimately it is a pattern. It's just sentences in this specific case, but symbols can be images, symbols can be whatever you want them to be. And ultimately, the idea still applies. It's just the way you create the associations, if you want, like the examples that you want to show to the neurosymbolic engine.
Yeah, very
yes.
nice. It's impressive that like with large language models, you could just give like few short instructions and it can work generically well for a lot of use cases. Like personally, I mean, I'm glad you talked about the ARC challenge, the abstraction and reasoning corpus challenge. Leo, you mentioned that. So for those who are not aware, it's like you're given like 2 or 3 different examples of the input grid to an output grid. The input grid can be from 3 by 3 squares to 30 by 30 squares. Each square can contain like a different color, up to 10 colors. And you also map like some pattern, like shift the square from the left to the right, or gravity moves all the blocks downwards. The pattern is not given in words. The pattern is given by the input and the output image, and you need to infer it. So LMs are surprisingly good at inferring input-output relationships from that few shot prompt. Okay, but based on my experiments with large language models, the zero shot prompt, which is that purple color text, is very important because there's so many ways to infer input-output relations. But that purple text, if you can codify it in words, sometimes just that purple text alone is enough. Like the zero shot is enough.
Of course.
But
I mean, it's also for humans like that, right? I mean, I can give you an example. I just say, like, look, this is the same thing as that concept, mathematical concept. You might even get it immediately. Like, you look at it and like, yeah, I see what you mean. But sometimes we would say, like, I don't get it. What do you mean? And then you give it some kind of grounded examples and say, like, look, you could port this over, you could transform this way, or some few short examples, how this associates. And then you're like, now I see it. Right? This is kind of the same idea.
I mean, all of this, I believe, and I've seen, I think these days, like the senior researcher from NVIDIA, I don't know his name right now. I don't want to butcher his name, but he posted like a very nice tweet discussing Sora from OpenAI, and basically what he said was that similar in the case of the physics that you see in Sora, he made a parallel with large language model. And what he said basically, I mean, this is the idea, right? That you see this emerging things with doing large scale language approximation, if you want. So, I mean, I'm not surprised at all at this point that you have all this, let's say, that it manages to capture these connections, because even in the paper, we said that large language models, we believe, are like a language control layer that you can apply in your system. And that's because of all these statistical patterns that we captured in the language. And again, that's not language and how we use language. We all probably agree with this, but it's working as an approximation very well. And it has these emerging capabilities that would allow you to use these associations between stuff in a few short manner, like four examples, which is that's interesting. It's at this point is no longer surprising, I would say, but it's very interesting that it works.
Yeah,
Exactly.
it's still impressive even after using it for so long. Like right now,
Exactly. Yes. Yeah.
a lot of things that I code the LLMs for, like to solve the UP challenge, like even my upcoming agentic framework and so on. All this basically, like, you just need to give it the zero-shot description, and maybe if it doesn't work because like maybe the training distribution is different from what you want it to do, you just need to give one example and it works wonders. If one doesn't work, you give two. But the thing is, just this flexible way of programming using as a zero-shot or that purple text in the DSL prompt is impressive. Actually, I have a question, because personally, like I've been using like OpenAI LLMs quite often. But I mean, given that Symbolic AI also interfaces to Wolfram Alpha and like other logical solvers, like how would the DSL prompt look like for Wolfram Alpha? Like,
We have an example also in the benchmark, but the idea is like you would ask it to, because it knows about Wolfram Alpha, the syntax of Wolfram Alpha. So so the idea is even here that it's easier if the model knows the syntax of the target language. So obviously, if it would be a totally new solver which it never saw or so, then it's like that's a problem maybe. So you would have to fine tune it also on that, because this is maybe one thing that we all have to acknowledge and keep in mind. We're not like large language models are good at, in my opinion, interpolating between two concept spaces. So like you would have like both concept spaces are learned, and now you when you do this one few shot example or whatever, and you say like this is equal to that or whatever, then you kind of have a nice way of interpolating, because when you start extrapolating, that's also when LLMs kind of like really go AWOC, like when they have to find out physical concepts or something like that, because it doesn't know anything about gravity, it doesn't know any, or when it has to like execute the mathematical formulation, and then it just guesstimates whatever the answer is. Sometimes it's correct because it was maybe also again within its training distribution, but oftentimes it's just wrong because it just guesses some things together. So this is kind of the idea. What you would use now, the LLM, you would say like, look, you know the syntax of Wolfram Alpha, right? So why don't you just try to port this over the most logical way, how this would be from a full text to a mathematical formulation. And this is where the community, I kind of feel, has to focus also in the future to tune this transformation. So it's basically just like a rewriting system from a full text representation to a math formulation, because then you can use that math one-to-one, just plug it into Wolfram Alpha, you get the answer, and then you're like, ah, cool, or Mathematica or whatever you use, and then you basically get the answer back. So this prompt looks like really just a rewriting, rephrase, and maybe 1-2 examples how this transformation.
To that diagram again.
Yes.
So in this case, if let's say I want to pass to Wolfram Alpha, I will still go through an LLM first. Is that correct? So I will need to pass the expression via few shot prompting by an LLM in this DSL prompt to get it into a format that Wolfram Alpha would accept.
Yes, exactly.
So that means I will need to give some examples. If let's say the training data for the LLM doesn't include Wolfram Alpha, I need to give some examples like, okay, if I want to ask for weather in Florida, this is the prompt to give Wolfram Alpha. If I want to do this, then this is the prompt. And so it's sort of like a wrapper or like a mapper from a free text or from whatever expression you start with. You wrap it into a format that the neural symbolic engine can accept. So
It's
I mean, with Wolfram Alpha, it's kind of easy because he also
yes.
uses the
syntax, is it?
the language. Yeah, so it basically most of the time you would see in our framework the way we use Wolfram Alpha is exactly like you either try to rephrase it, like you do like a symbol rephrasing to make it let's say in the style of Wolfram Alpha, but you just rewrite this text to match the prompt of Wolfram Alpha, but that's usually natural language. So you can even try directly to pass it to, let's say, trim a little bit or filtering it, and then just pass it to Wolfram Alpha. If it's a formula directly, then
Yes.
it's
If it's not, then there is exactly what we called here with the in-context associations, because what you would, or the domain invariant associations, because what we basically also can do is we can have like an, let's say you have a language that you're grounded in and the model knows about, let's say SQL, for instance. So you have basically SQL language, and maybe now you might have your language that the model never seen before because you kind of developed it right now, right? But if there is some similarity to SQL and the behavior of like, query language and so on, what you can do is obviously do again this associations between these two languages. Say that these keywords, look, it's called fetch in this new language, but it's called select in this other language. It's called project in SQL maybe, or whatever, projections and so on, but it's called in my framework differently. I don't know, right? So you could just associate these keywords and try to say like, now try to apply all the logic from SQL on the new query language that I just evolved, because all the other operators, larger than, smaller than, everything else is kind of like the same. Just these keywords are a bit different, and these are special cases. You could also put all that in. In this case, you're kind of obviously you have to be careful how far you then extrapolate, again, as I said before, right? Because the model will just guess everything that is in SQL is valid in the other language, right? But to some extent, this is at least working, that you could do this transformation, and then you could use that transformed version again and then evaluate it with your system, which is really nice. But be aware of this extrapolation problems that can occur afterwards. Anyhow.
Nice. Actually, before we move on, yeah, because I just want to find out more about like how this process works. So the other thing is, let's say if you have a speech, like for example, you have a sound clip of a speech, and then you want to do speech to text recognition. So if we apply this same 4 steps, I would imagine that the clip could be the expression, right? And if like, for example, the sound clip, is this like how we interpret it? Then there's no DSL prompt here because we don't really need an LM to interpret that. We just pass it through the speech to text program, which is the Neurosymbolic engine in this case, and then out comes the text.
Yes.
So there are multiple ways to do this. You can either add a description of the symbol. So like you can you can make it be a symbol that represent images, let's say, or it can be type-based. Like you can create a type that is an image, or a type that is, yeah, let's say, let's continue with image. You can create a type that is an image and basically is the sound wave pattern of the speech. And you can use that and even associate to that image the actual, let's say, text that it is in the image. So that's the nice thing about it, that you can do this kind of things.
Or the simplest representation. There's one more simpler representation which we actually use in the framework very frequently is usually you always have a path, right? So when you would talk about like there's a sound wave, as you said, right? Usually it's still stored on the file system. So you give it just a path to the file. And the easiest way to determine like which kind of, engine to invoke, for instance, even for the first manipulation, would be just look at the file ending. That's the easiest way how you could say like, that's a wave, because then you use the speech to text, as you said, then we have a symbolic form, then we can go on with the next processes and so on. So these are kind of like
but don't use a classifier. Don't use a classifier there, because Google just released the other day like how to find extension to the files. And one friend of mine just said that it gave it a I don't know what file, and it said that it's a torrent. So like
yeah, sure. But I'm just saying as an example. Yeah, Just of course you can always manipulate this and hack this around that it doesn't work, or the other way around. You could change file endings. But yeah, this is a very simple example. Or you could also read the first bytes and so on and see like, okay, this is maybe associated with this and that. And that's why we always talk about neurosymbolic backends, because this could be just very deterministic first processes, right? You don't have to throw everything at an LLM. If you would have the engineering power as a company and so on, you would sit there, write some rules, you know, how you would process different file formats and so on. And then you basically just if else if you want so, and then invoke the corresponding engine and to get always a valid symbolic representation back.
Nice. So as we move on to multi-modality, you see like Sora and everything. Let's say we have image. I've heard that you can put the image as part of the symbol, right? Audio, I suppose you also can embed an audio file in the symbol, right? You can. So
yes.
the symbol be a file name that interprets by the file extension, as what you mentioned just now. Is that how you do it right now? The symbol is a file name.
If you have, for instance, everything combined, so you would just have a full text and there is one file or so, then we know that we have methods to parse that out and say,
so when you process that symbol, next time when you see a file name in that symbol, you will extract the stuff from that file itself.
Yes, exactly.
Next time, if you have a video processor, you can put the video.mov.mp4, you can put that inside the symbol itself. So
yeah, we have that in the vision with GPT-4 vision. We have that where we sample frames from the let's say again, you will have some, you know, MK4 V or whatever format and so on, and then it sees, okay, this is a video format, it loads that and then basically samples. I mean, obviously the context is limited, so we're sampling kind of like, I don't know, 15 different frames or so along. If the video is super long, then obviously they might be just snapshots of it. But obviously the smaller video or the GIF or whatever you use, because you could also use GIF, for instance, as a format, then I think with 15 frames, you get the main gist of what is in the representation.
Oh, that's very powerful. Actually, I like this a lot. Maybe we take some time to emphasize this. This symbol is not just text. Okay, it could be multi-modality. It could be audio, it could be video. But I think
it could be a complex pattern.
It could be a combination
of complex physical pattern. Yes.
It could be a combination of all different formats, right? You just need to specify which files you are referencing to.
Yes. Right? Yes.
Yeah. So it's very flexible. It can be used to integrate in different kinds of neurosymbolic engines that process different modalities. And I do think symbolic AI is in the right state in the world right now, because we are moving to multimodality, image, audio, video. Soon we will do all-in-one processing. So I'm happy because symbolic AI is in the right place to take advantage of the different kind of engines that are available in the future.
Thank you. And this is actually, and the nice part is exactly as you said it. I mean, right now you would have if-else statements separating in your backend, right? This is this file, then do this engine, then do this engine. But that's what the beauty is. Let's say the models become, as we see with you know, GPT-4 vision and so on, and all the other models, also Gemini and so on, 1.5. You see that they become multimodal because their context extend, and now they basically just tokenize the images directly in context, right? So you don't have to do the if-else, like switching in between. You could just swap the neurosymbolic engine backend, and they just say, now I have one model that just can tokenize everything in one sweep, right? So this would be, you just have to load maybe the file in between because you had just a file path or so.
So you don't have to change the symbol, basically. You just change
exactly
how you interpret the symbol by the engine or by some inbuilt functions.
Yes,
and change
that's the beauty of it.
System.
Yes, yeah.
Yes.
So this is in context domain adaptation, or what do you call that? I think domain independent.
Invariant domain invariant associations. Yeah.
Very, very nice. Okay, yeah, I think that's beautiful. Yeah.
Yeah. So thank you. Yeah, and the last part is, I mean, we are all a bit accustomed that you also asked me at the beginning with LangChain, but we ground ourselves like mathematically a bit, and we call this function composition, basically, where you can have obviously different functions stitched together. The only tricky part you always have to be aware is about domain and codomain, obviously. So when you do the transformation, and especially in the multimodality, as we talk right now case, this might vary, so the support might vary a lot. But if you're a bit like more lenient and accept this kind of transformations, then you can stitch, obviously, you can create a computational graph, which is a multi-step generative process where each node in the graph could be either coming from a large language model, could come from, you know, any mathematical or any other like engine and so on. And you could just, you know, transform from one step to the other until the end, where you have then your result from the symbol, right? So this is kind of like, I think chaining, or what LangChain, what they do, just with like different modalities, different engines, different, and always grounded in symbols back, as we talked already. Yeah, then the paper also offers a bit some details about the typing system and representations, which I will not dive too much in there because we can look at the code later. But it's kind of like, just to give the analogy, Python has object as a type, base type. You can think of symbols being our base type, and then you basically have the first inheritance of a symbol as an expression, because you can always evaluate expressions to reduce them again to a symbol. And then every other functionality in the framework is just deriving from expression. The expression, that's the only special thing about it, has, or not the only, but it's one of the most special things about it, it has like a forward function. If you think about this, like in PyTorch, you have the forward method, to be more precisely. So you have to implement the forward method when you try to evaluate, you know, the symbolic form, to reduce again the expression to a symbolic form.
Actually, there's a lot of motivation from math here, like, right? Like a symbol is
Yes.
like maybe x plus x is a symbol. Then
Yes.
expression is like x
No,
plus.
that's an expression already. So it's, you have x and x are symbols, and then plus is already creating the first expression, and then you try to expand. But yes, exactly, that's exactly expiration.
And then now with multi-modality, expressions can be even more complex, like transcribe this audio, or the
Yes,
expression could be even
exactly,
more
exactly.
stuff like, I mean, in fact, it might even just be like an image. I mean, there's a lot of things that could be an expression, as long as it
Yes.
allows you to interpret something, like and evaluate something to get a symbol. That's an expression.
Yes. So that's actually the beauty of it, because I mean, you have usually a symbol, and as soon as you have a prompt, right, or any operator, right, you kind of create already an expression, and it could be full text. And that's the beauty of it compared to the, you know, to the 60s, 80s, let's say 80s, where they kind of like faded out symbolic forms, where they said like, oh, okay, they don't generalize that well, right? That was the huge problem that was missing. The missing link was, back then, it was like, symbolic methods never took off because they had not this flexible interpreter, if you want. So, or as we call it, the LLM for us is like a semantic parser, right? So, because it's semantically augmented and understands the context and can use now this kind of, you know, flexible ways, even texts, right, to operate on the symbols. And this was missing, and then you couldn't like scale it up with having just this if-else statements, you know, there's huge lines of like, how do I do this and do this condition and so on. So, but now with LLMs, it's like, this was the missing link, where we see again symbolic forms researching. And what we like about the symbolic form, or LLMs in general, is like, think of it, I always like to compare it to vector quantized, you know, autoencoders. I like this analogy, just analogy, but the idea is like, you have some input, you have some output, which is again the same domain, but in the middle you use usually this bit binary vectors, right? Where you said like, I encoded the information, I quantized them in ones or zeros, and then try to create, you know, to generate again from that. But if you think about this process, and now swap the binary vector with a symbolic vector, if you want. So with any full text description of your task and so on, you could see this as a generative process, in the sense that you have this vector or this symbol in the middle controlling the process. And now you always have, you know, input, output. I mean, domain and codomain may vary right now if you have multimodality and so on. But the idea is like, you have these transformations from input to output, and just always grounded in the symbolic form in between. And you can interpret it as a human. That's the beautiful part about it, because now you can, if an operation doesn't work, because there are many that don't work. So don't get me wrong, there are many flaws of using this, right? And we have to tune these LLMs in the future much better to do these operations. But if you like, something goes wrong, you can just look at it and say like, look, my prompt was correct. This was correct. Okay, why didn't it work? Well, the model is obviously not affine to do this operation that well. So you just have to get more data, collect more data, fine tune this operation, or just in general, the entire model, right? Class. So this is actually very beautiful now to have an interpretable as they always say, explainable AI, right? So to have an explainable layer in between that kind of tells you what operation to A to B actually, or what transformation from A to B actually was in between, right? What was the expression itself?
Nice.
Yeah. This is how we see it forward, to have in the future controllable computational graphs that we can interpret as humans, not just vectors. Because if it would just, you can't bind everything in the vector space also. You could think about it this way, but then you can just look at floating point numbers again, right? So you don't know what to interpret.
Yeah, so by vector space, you mean embedding space, right? Or you mean the embedding
Yeah, exactly. Embedding or vector valued representation.
or an embedding of an image and so on.
Exactly.
But in this case, the symbol is not the embedding. The symbol is directly that domain is from, be it text or be it image or video. And this vector space, you can derive it if you pass it through some embedding model. I mean, of course, the LM is an embedding model in some sense, because you can use the LM to compare text similarity and so on. But we don't store that embedding inside the symbol because it's very confusing for humans. You want this symbol object to be interpretable by humans. You want it to be at the end form already, like be it text, image, or video. Did I say it correctly?
Yeah.
Yes.
Exactly.
Yeah.
It can have multiple representations. The symbol, like, right? It can have, like, you might give it a feature map from a, let's say, from a model, from a classification model, from a like classical, let's say, ResNet feature map layer 50 or whatever, which is a filter for whatever. You can store that as a symbol, but you can make a description of it, and you can operate at the description level with that symbol, which is very powerful.
Yes. And yeah, and the rest of the papers, so in this framework section, we talk, like I said, the typing system, then this polymorphic context that I already mentioned before, where we even have this example with vision tag, as we talked earlier about audio files and so on. So you could say, like, look, there's a vision tag in here. You just have to resolve this every time you see this kind of representation.
In fact, it's very flexible, because in the future, if something that is beyond audio, video, maybe there could be a future format called VR, when VR takes place. That you can just put inside your meta text. So it's very flexible, because no matter what comes out in the future, what new formats, because ultimately you can still represent them in some file, right? And then you can pass it using this meta text.
Exactly, just have done a different tag maybe as a representation, and then you, during the parsing process, you look at the file extension or whatever method you use, and then you just know how to replace this.
In fact, I like this a lot, because it can be a very complex, like it can have 5 or 6 tags, but maybe if your neurosymbolic model just does text, then it will just ignore all those texts.
Exactly.
If your engine does images only, then it will just look for the image text.
Yes, exactly.
Yeah, so it's very good. You already filter by domain in some sense.
Yes, exactly. And then we have this operational methods, which are also like a custom. So in this graphic, for instance, we describe how we create these operations and methods, basically, where we have maybe some user data or arguments and so on. So the user input, maybe even some attachments from as a like a payload from previous executions. Then you have the symbol class, or in this case, the instance, the object. So you have the symbol object instance, which has the kind of different attributes. And here above, I talk about polymorphic context, meaning in the sense, how do we create this kind of polymorphic behavior? It's basically by just grounding the model in, let's say, a static context and a dynamic context. This is maybe equivalent. So the static context, you can think about maybe system prompts. So when this was introduced back then from GPT models and so on. So this would be like something you're at design time, you decide this class or this symbol behavior is grounded in this kind of context, right? So it's, I don't know, you are an animal and do this and that, and it's basically your derived symbol, right? Which is kind of very animal-like, or expression that is very animal-like. And then you basically have dynamic context, which can be updated at runtime. So while you're doing the execution, you could basically add some additional information. And then you have the different operations attached to it with the operation description. and then different fields of examples, as we talked about the templates. And here you see the full pipeline, how this gets resolved. So basically your custom method, we have some standard library where we use some decorators to do this composition of functions. And then you have a pre-processing step, an engine, a post-processing step, and apply then some constraints. This would be, for instance, in your library, John, the JSON, for instance,
The
constraint.
JSON library, right?
Exactly. And then you get the output. So this is like to try to ground the entire, give a top-down view on how do we do these transformations from symbol, then expression, and then how do we resolve the entire pipeline through multiple, technicalities. You can look this up also in the framework. But yeah, this is basically the high-level overview. And what is super interesting is actually...
Wait, before we move on that, just
yes, sorry.
question on maybe you zoom into the graph on the right, the input all the way to output. So just some design considerations here, just to ask. So I understand the input could be like an expression, and then like, what's this decorator here? Why is there a need for this?
So this is a technicality if you want. So we talked about like quickly composing and prototyping different types of symbol or if you want functionalities. And the way that we came up at least was for us to write a library, basically like the core library for us is basically few shot. But you might have already like a summary few shot, a translation few shot, or some different kinds of already operations. And to avoid to cram everything into symbol, right, or the derived objects from it, we thought about abstracting this out and saying like everyone can use our framework the most flexible way they want. So if you don't care about all the symbols, manipulations, and everything about that, and you just want to have an LLM in, let's say, one component, one method, and you want to just have this few shot example, you can just easily use a decorator from our standard library, tag your method if you want so, and from that point on, this goes to the Neurosymbolic backend. The second nice part about this is why we did it this way is control flow. So we wanted to have actually, if you have, let's say, any decorator on top of your method that you kind of defined, your custom method, you put this tag on it, that basically you're executing the Neurosymbolic backend. You come back. If it fails, for instance, if an exception fails because the constraint has failed, the post-processing, whatever, it can a lot, or the model is just the API is not available, right? Then basically, if you have a default implementation, then you could basically just fall back to your default. If you would be like, I don't know, do it the classical way or just some approximation way, then you just do the classical implementation, say like, look, this is the result, sorry, it didn't work or whatever, or this and this was the default result. But if it works, it's obviously prioritizing the Neurosymbolic backend. So this is kind of like two choices with more technicalities if you want. So why we did it this way.
So
Yeah,
actually, just ignore the decorator for now, because the decorator will also go through the same flow, right? I mean, decorator or not, you will need to go through the preprocessor engine, post-processor constraints, and output. It's just the decorator does it for you automatically.
Yeah, but it also selects which engine to use and so on. So there are multiple technicalities behind it, because if you use FewShot, obviously it uses a Neurosymbolic engine. If you use a search, for instance, a tag, then it uses already by design, let's say Google, for instance, SERP API, for instance. If you use different other like decorators, have like for Wolfram Alpha and so on, there is also I think expression or interpret the decorator and so on.
I get it. Yeah. So basically, for people using the Symbolic AI framework, it is recommended for you to just use the decorators because like it's already built, right? Like a lot of different things.
It has a lot of functionalities, but
Yeah,
if you want to really use the full power, you should use the symbols themselves and expressions that we write. So that's the most abstract form. You don't have to care about all decorators and technicalities. Just to use the most abstract form is just use an expression that we wrote, or stitch them together or whatever, and then just execute. Sorry, Leo. Yeah, please.
Yeah, what I wanted to add is that in the, let's say you have a very specific case, the decorator is just a mapping of composition in Python. So you can stack, so imagine you have a function, you just define a function, and then you can stack on top of that function and decorators. And what that means is that they chain together until the last execution. So
Yes.
that's a nice, if you want, at least to us, it's a nice syntactic sugar
Yeah,
kind of
and
formulation that
exactly.
you can make.
I like that sense, syntactic sugar also, because you don't want to bloat your code. That's also the next part, right? So
And it's
that's what I
also like
said.
principles of software development, like separation of concerns and like all these
Yes.
things. Like why would you bloat everything in one? Be functional, guys. Don't write code that nobody will understand.
Right.
Just write components that everyone can understand.
So the decorator, you can put it over your function to execute the. Actually, what do you put the decorator over? It's over a function, right? You put the decorator over a function, and you will execute the whole
Yes.
pipeline that is shown here. The
Yeah,
whole
exactly.
pipeline constraints and so on. The
Yes.
next question is, things will fail. I mean, is there an inbuilt error correcting mechanism that you have built such that if, let's say, the constraint fail, will it retry again? Like how
There
is it handled right now in Symbolic AI?
there are implementations of neurosymbolic backend, for instance, where it retries with, I don't know, 2 or 3 retries with self-prompting and so on. So we'll say like, especially that's useful in cases with coding, for instance, where it kind of fails to create a workable solution, if you want so. But most of the functions right now are like, we don't want to influence your control flow at the most. So we don't want to like interfere with your logic. You can write it yourself. We have some like try expressions and so on, and we have some expressions that are dedicated to retrying, basically, so we can wrap them around other expressions. I think really like PyTorch. You can write one module, right? And then you can basically just wrap the module around some other module, and this way it gets a try except block around it, and self conditions it when the execution didn't work. This is when code execution is, for instance, invoked, meaning that you generate code, you execute code, fails, and then you get basically back the answer, compile error, whatever it was, or execution error, and then you basically just retry again.
So I basically there are some retries already encoded in, but user is free to add in more themselves.
Exactly, and we try to more like less influence the at least as possible influence the execution flow, because you want to have the full control of the execution flow per problem you want to solve, right? So, but we have like
We just give it the Lego blocks, right?
Exactly, kind of like that.
But I like this a lot because it's very flexible. Like from any input, you can just map it using your like preprocessor to the engine's input. After the engine comes out and output, you can also map it back to what you want using the post processor. And all these
Yes,
are fully
exactly.
customizable.
Yes, exactly.
Yeah, and this whole workflow of preprocessor, engine, post processor, you can store it as a fixed block or custom block that you can just call it next time. So it's very, very I would say it's reusable because you code once, you can do many times. Or actually, honestly, I used Symbolic AI before. You don't really need to do all these steps. You just take the preview block.
No.
It's good enough.
Yeah.
You just take the preview blocks, unless you have a very specific use case. If not, most of it is already pre-built by Marius and Leo.
Yes. So you have to think really, because what task you're trying to solve. So this is maybe exactly the task that fits best. Self-referential structures would be defined here. And here we like in self-referential structures, in programming, this would be like a struct, for instance, where you have in the struct itself referencing it, right? So it would be like the class has self-reference to itself, right? And can you can nest this and do some traits with the execution and so on, or with the references. Why we talk about this now, or how this connects to the example above, is you still need like a very dedicated format when you do this kind of like if you want to have an LLM that has an LLM in itself, in its context, right, and knows that it can use it. But then when it uses it, you also maybe want to have a very dedicated format, the way it outputs things, right? So this way, you will then really have to sit down and think about how do I pre-process it, post-process it, and constrain it to get the right results. Otherwise, I have to retry and so on, because otherwise your execution flow will fail. Obviously, you could fine-tune it at some point, but we all know there is obviously if you would do this for every task, then you would have to create one fine-tuning function for every specific house, which is also like bothersome. So it's a way how to control and constrain your output and massage, if you want, so that the data in that way that you get what you would have expected. Yeah. And maybe now to also go deeper into self-referential structure, this is actually a very interesting concept, also introduced by Schmidt-Huber and so on. But it's think about it this way, like you can write meta programs if you want, so like that. That's actually one of the most coolest parts of symbolic AI. You can actually have a control layer, which I think we have in the appendix, I think a graphic for that. Maybe if you may quickly scroll down. Do we have it somewhere? Yes, here. So you can have, for instance, you as a user, when you program these expressions and all these things, you're currently at this point in time, you're mostly the one that does this control flow and computational graph. You're programming something together, you have this graph, you execute it, good, it works. You could have obviously some knowledge base, maybe, meaning that you could have some, some conditioned on some code, knowledge representation, some graph, whatever, from your other applications, which can kind of create this computational graph for you as a second step, if you want so, and then execute that. But also the idea in the long run would be that you could have agents, as you probably know, or meta learners, if you want so, that understand basically this abstraction. So they understand the meta program, and then they understand this expression language, and then they create these expressions and symbols and so on, manipulations themselves. So meaning that a meta program could I like to think about this in the way of, what is it called? The concept, doesn't matter. Sorry?
Oh, no, I was thinking whether you were referring to some like self-learning systems.
It is in that direction, but the one word is missing for me, but doesn't matter. The whole point is not to describe like intelligent programs in like if-else statements or whatever, or just program it down. I don't think that we will manage that because the complexities are way too high. But what I believe that we will manage is to write a meta program that understands how to unfold and evolve basically these subroutines and programs over time. So basically where you might describe
it's metacognition.
Like,
right?
metacognition, exactly, but metamorphism, or what is it called? I forgot what the technical word is, but anyhow, where you have it doesn't matter. Anyhow,
the gist is that the program can modify itself based on
yes,
what
exactly.
Yes.
Exactly. So you just describe basically how does a memory work? How would you basically unfold this over time? And then you basically can just, run the program that it will figure out how to use the memory most efficiently, and will figure it out over time.
So
this is
new experiences that the program goes through will be stored in its memory, and the next time it runs a decision, makes a decision, it has access to this memory, and then it can change its decision based on something that has happened in the past. Like that's the idea of
exactly.
idea of the method. So it's learning from experience. And
exactly.
I like this a lot. I mean, I also mentioned back then in a few other videos we did that I think this memory is going to be the future of learning, because like how we learn is heavily influenced by what we have experienced before in our memory, how to store the memory in different forms. I know symbolic AI has short-term, long-term memory, but I'm also talking about other forms of memory, like be it conceptual space, like relations between like person A and person B, or is it like text space, directly free text, or is it in a summary space or reflection space and so on. I haven't quite figured out which space yet, but the idea that there's many spaces that you have for memory and you can just refer to them to make a decision, I think that's powerful. And symbolic AI would provide the framework to store these various forms of memory as well, if I'm not wrong.
Yes. Yeah, thank you. And exactly, that's kind of the idea to how we also see self-referential structures, because obviously there could be a meta LLM that understands the meta program, but then it knows that there is an LLM that it can use and instruct, and it basically just instructs itself just in a different kind of way how to utilize itself, right? If you want. So this is kind of how where the meta learner creates your corresponding operation, the language interface gets this input and the language model basically processes it, and then you get again a result condition, and you might just create another operation and so on, or you might use a tool or whatever on the side. So this is kind of like how we depict this or see this in our framework. Yeah.
Is the learning purely on memory, or are you also thinking of learning via fine-tuning?
Both. So I say in both are the strengths as the picture at the beginning highlighted, because sometimes it's like, as soon as you figured one problem out, maybe the mapping from input to output, sure, you could go through the entire composition again and do these transformations all the time, which is a multi-step process. But if you have input and output, you can just conflate both of them and just say, like, why not just map directly from input to output in a specific function that solves exactly this purpose? So you could even instruct learners, for instance, to figure once out the path, right? Or you can create yourself the expression if you want, so the long one, and then do the generative process, the multi-step generative process. But then at the end, you get the input to output mappings, and you say, like, why not just fine-tune directly a very
input to output mappings, right?
Exactly. A very, very slick, maybe even a smaller model. You don't always have to use the GPT, whatever, but you could just use any 1 point whatever 3 billion parameter model or so, like which is much more efficient or faster optimized, for your machine.
I like the idea. So I
This
would like to advise people on fine-tuning and using memories that, like, if you use fine-tuning methods, you might lose some general capabilities of the model, because when you fine-tune on your data set, it doesn't do as well. But if you want to fine-tune, you can fine-tune on only a process that the model would see. Like if it's just input to output for a particular process, and the model won't change to do other parts, I think it's okay to fine-tune as well, like just for that specific process.
Yes. I mean, it's more efficient. That's the whole. If it's about efficiency, if your mapping is already deterministically, and you can have this as an operation within your context again, right? Think about the functions within context. You could once do the expressive long way, but then you have collected enough data to fine tune, a specific function, which you can append again to your context and just use that for the transformation through Wolfram Alpha, for instance. Why would you instruct that in a very verbose way? If you did enough mappings, right, you could just conflate that to one operator that can, just when you call that one, you get always a mathematical formulation back for Wolfram Alpha or whatever, right?
But for this,
concrete
fine-tuning is not implemented in Symbolic AI, right? You're just saying that this is possible to train your own LLMs and then use it to
Yeah, we're working on that. That's one of the future outlooks.
How about the memory part? Is the memory part implemented already? Like based on what you have seen, like when you call engine and then the output comes out, some errors and stuff, or like when it succeeds, do you already store it into memory? Or
we have memory implementations, yes, where we store, like I said, most of the things are context free if you want, so like memory free if you want, so right. But you can obviously, we have modules in there where you can have like obviously sliding window memory if you want, so you can also have more complex memories. And also in our benchmark that we kind of did the experiments, we had also like, we have a memory which we update to detect how we do the next scheduling and so on of the next task. So yeah.
So I would say that this paragraph on self-referential structures is like what a potential use case for Symbolic AI, but it's not natively implemented yet, right?
No, it is implemented. It is implemented. We have in context associations and so on with like with LLMs and functions and so on, and we also have memory modules. I'm just talking about if you have just simple expressions and so on. Like if you just use expressions and so on, there is not one expression just doing the memory thing. You have to combine them in a functional composition, right? That's kind of the idea.
But it's also about the realization, because if you think about the persona examples that we did,
yes.
You can have two personas, and the third persona can be your meta, let's say your meta agent that supervises the other two. So
yes,
I would say that the self-referential structures, it's exactly what it means. I mean, they are structures that you can realize if you have the right tools. And in this particular case, SymbolicAI allows you to create self-referential structures. And one example of a self-referential structure, if you want, is the personas in which one agent supervises the other two agents, or like one agent supervises one agent, or you can have even more fine-grained self-referential structures in which basically the class itself, it's reused every time if you want to be like, let's say, more programmatically. So it's just about realizing self-referential structures.
Yes. And in the benchmark, we have the self-referential structure where we have the meta program doing the task, like unfolding the task, basically how we want to execute. This is the meta program if you want. So, and then the one of the sub programs or sub processes are basically using the LLM to do some prediction on whatever a task.
Yeah, it's scheduling and task execution.
Exactly. So these are also like exactly self-referential structures that are already realized, where you can look at examples how we did that. But it's obviously not one expression or something like that. It's like then you have to find compositions of how do you want to have your execution flow, right? And this is the crucial part.
Probably you can abstract away, like you can create an expression that would be general enough to create, like, to cover a lot of self-referential structures that you would want. Sure.
I mean, conversation is a good abstraction, I would say. Conversation has a memory in it. It doesn't have toolsets by default, but you could put them in there, and then you would have also a self-referential structure with memory.
Then example that you can give for like one self-referential structure. Like this time you were talking about conversation. Maybe you could give a more concrete example of how symbolic AI would use this self-referential structure in that context.
So it would have like in context, like Symbia, for instance, our chatbot that we realized has basically the capability to just, detect what is the current execution, what is the context, what it wants to execute, and then basically take one or the other path to use different tools, which one of the tools could be again an LLM if you want.
Okay, so this is actually more, okay, it's not exactly self-referential, it's more like it's context aware. Like it's aware of what context has gone on before that and use that context to do
it is self-referential because you could have a memory also attached to it. So you could also know exactly what the entire execution
I got confused here. When you say self-referential, it's always like thinking I'm in a loop, in a loop, in a loop. But I mean, in this case, it's actually still a sequential execution. But every time you do the sequential,
it's recursion. But no, it's recursion. And that doesn't have to be necessarily a loop. Recursion is also self-referential. Like a struct has a struct in it, has itself struct. That's kind of self-referential. In
the LM basically can call itself to do a task, right? Like so that's a self-referential.
Yes, and you can obviously pass on also the memory. You can pass on every experience if you want, so, or any other tooling or whatever you can combine into this functionality. So this is where how self-referential, at least from programming, at least from structures and so on, comes, and how we apply this on large language models in that sense.
So like in the Symbia case, the self-referential part comes in when like at every step of the conversation, the memory is updated. But the Symbia chat is still the same agent that is giving you the response. It's just that it has enhanced context now.
Yes, it has enhanced context, and it uses maybe even sub executions that is also referencing our own LLMs and so on, if it needs to do a sub process.
I mean, the tools that is equipped with can also be an LM. So it's like a LM in an LM in an LM, that kind of structure.
Exactly, that's what I'm trying. That's the recursively self-referential.
All right, I think the name here is a little confusing. Yeah, maybe if I have a suggestion, maybe you don't call it self-referential, because self-referential has other meanings, like I call myself. I mean, in this case, yes. In this
I
case,
see your point, but yeah, the names are always
structure, right? If you think of it, like it's
but one important thing is that if you basically, so it's no longer a self-referential structure if you have two large language models. That's no longer a self-referential structure. A self-referential structure would be if you use the same, let's say, neurosymbolic engine, which would process its own inputs and would unfold based on itself, if you want. It just computes and unfolds the chain of execution by itself, and that's why, I mean, in the benchmark you have the scheduler, which the scheduler can be a large language model, which can also schedule itself and also like execute the tasks that itself scheduled. And then it just does this until it ends.
Okay, I get what you mean here. It means that you have one meta planner that does a lot of things, and then it can plan for itself, it can execute itself, it can
Yes,
summarize the output
exactly.
itself and so on.
exactly.
So
But if
it's
it's two, it's no longer the same, because that's no longer, if you rely on another large language model, even if it's like the same, you instantiate it differently, then it's no longer a self-referential. Self is just instantiate your
Yes.
neurosymbolic engine unfolded
but
with
don't you
the
agree
right
that-
structure.
Don't you agree it's more like calling your subsidiary components of, let's say if an agent has like 5 functions, you're just calling the functions one, or you're just calling function 1, then calling function 2, then calling function 1 again, depending on the previous context. So it's not exactly referring to itself, it's just that it hasn't finished executing yet. It's just doing a step-by-step execution. And then at each step, you just choose one of its available tools or functions to use. Like, wouldn't you say it's
but
Yes,
the
but
function,
that's only
but the
the tool.
functions,
That's only the tool choosing.
the function
What if you
itself
don't
has to
choose
have
tools?
the LM. Yes, exactly. That's what you're missing. So, I mean, we can talk about or look at this in details if you want later on. But the references, like if you really look at self-referential structures from programming, you will see that you might have a struct of a node where you have in the struct of a node, let's say a pointer towards a struct of the node, which is itself. So this is like where you can really just loop it itself. It's the same struct, right? And why you do this is usually when you want to make a linked list, for instance, or something like that. So you would, in a programming case, you would just, know that you can just the pointer within itself can point to another instance of that struct, which is again, the next data element. So this is, in this sense, is also in here because you have the LLM, which can have as the meta program, as you said, or in general, it could just be one program. And then it basically has a reference in its own context that it knows that there is an LLM, which is itself, right? Or the structure of itself, if you want so. And then you could, by fork,
I
you could say
understand what you
like,
mean. Basically, you
your
are just giving it as a tool or a function. You're giving it itself as a tool or function.
yes.
And so
This
Yes,
is also
exactly.
already self-referential already. Yes, this
and
is
you can
already
call itself and itself and itself until it decides that that's enough. Then you can-
Exactly.
yes, exactly,
Yeah.
exactly, and that's important. It's important because in this way you actually have just one model, actual or model architecture, which is a neurosymbolic backend, as Leo pointed out, but it can be nested in its execution path in its runtime if you want. So, and self-point also with memory with other things, so you could augment it with everything you want.
When it calls itself, you won't pass it the same memory, right? You'll pass it a different kind of memory.
Depends
It's
on the
always
task.
updated. It's always updated at the next phase, right? Because you have more experience, right? From running a loop, then you run the same loop again, but you already run the loop, so you have some experience about what happened. So basically, memory always, let's say, it's getting updated, right? So that's why it's never the same memory.
Yes, but necessarily it doesn't have to be the same memory. It could be the same, but does not have to be. That's important.
Yeah, memory is just like memory is still like a tool. You don't need necessarily memory.
Maybe it's a bit beyond the scope of your paper, but I'm trying to create a hierarchical agentic structure right now, and I also have some issues when, like, if you call itself, like causes, if something like what you're describing, I'm trying to implement it out as well. I realized that if you give it the same memory as the top layer, sometimes you might have I mean, it's great to have the same memory. I mean, the context is the same, right? You follow the top level context. But at the same time, it can also influence the generation at the bottom, because sometimes you don't want to give it too much. You just want to give it enough for it to fulfill its tasks.
Exactly. That's why I say it depends on the task. So for us, it was
correct.
important to have the tooling that can resolve both problems. We can do both, and we have examples where we do one or the other. Yeah, it's depending on how you want to use it in the end. But the idea is obviously to enable it to have this self-referential structure itself.
Nice. I think we spent quite a lot of time here because this is an interesting point. I don't think we discussed much on this the last few times, but yeah, it's interesting that you could use the SymbolicAI tool and call the same tool as the tool that called it. So that's I'll say it's a feature of SymbolicAI, and those referential is different from self-learning. Just now we were talking about self-learning. We do have interfaces like memory that we can learn from experiences, and also
Yeah.
like if you store the various input output for a particular process itself, you can fine tune yourself externally. That one's not in symbolic AI, but you can do that externally for your own large language model. That's how you do the fine tuning learning. Yeah, we do have about 5 minutes left for this.
Yes.
So I think today, let's not do the evaluation. Let's have it on another session.
Exactly.
So maybe let's just like actually before you conclude, I just want to ask like a very, very curious question before I let you all conclude. Like, why did you all decide to open source this whole project? Since I mean it's going to be a company and all, like what was the motivation behind it?
First of all, we believe that contrary to all this, closed source movements in the last couple of years, it's important to include the community in this process, right? So we believe that there are general concepts, first of all, out there. We can't tackle all of them, like all the problems I told you a bit before. Like there are operations where the model just fails; it doesn't get it because it's just too complex or too out of distribution, so on. So you have to tackle fine-tuning in that direction, meaning also you have to curate data sets and so on in that direction. Other things are obviously a bit to combat movements as in OpenAI and so on, that they kind of close down. Other concepts, again, are to or ideas are also to help us evolve this system, right? Because we want in the end to have what we call as a company, as you said right now, we're kind of laying out the ground layers for a framework that basically we see as the quote unquote OS of AI, where we have all these different models and solvers and so in one coherent framework together. But this is a task, again, that cannot be solved by one or two or what even at one company, or it has to have a community backing it. So this is kind of like a huge project for us, and we believe that this makes most sense to involve the community to also be part of it, because only then I think it's realizable. Otherwise, it's just one framework amongst thousands and so on, which we might get lost over time. But I think the concepts are more, and the concepts are important for the community to be understood. I believe, at least. Yeah, maybe also.
I mean, some people might not. Let's say there could be people that would disagree with us. I mean, the way we build the abstractions and the way we build the framework. But I also believe there are people who would agree with us, and I would invite those people to come and I mean, the way I view this, it's very simple. I mean, Marius and I believe we found the right kind of abstraction for the framework and the right structure to allow building interesting things with the framework. But I would say that there, at least in I mean, just referring to me right now, but I know for a fact there are people 10,000-fold smarter than I am who would understand the abstraction, but can do it so much better than I can do it. And that's why we need this kind of people to come and at least like discuss or like, this is, don't forget that it started as a research project, and research is very important for us it's a core component, and research should be open source, first of all, because how do you make progress if we wouldn't have journals, and how do you exchange ideas? Like how do you make progress
with the current closed source climate as well? Because like from GPT-4 onwards, like Gemini or this, we have no access to like how they did it, and like we are actually reinventing the wheel a lot, because like different corporations try to guess what other people are doing and so on. Yeah, like I actually fully agree with the open source movement. Like even in my company right now, like I'm creating an agentic framework and I'm intending to open source most of it. So I want to embrace the open source movement because it's very useful to exchange ideas. I always think that humans as a whole, like our civilization, we don't progress individually. We progress as a community. So
yeah, there is this symbolic behavior paper from DeepMind, Santoro et al. It's a very nice, because it talks about symbols, and it talks also like about how symbols evolve in a community.
Yes, and yeah, it also creates relevance, right, on the long run. I believe that, because I mean, if we had this closed source and we do some magic and you just see some, I don't know, output, you wouldn't understand it specifically, as Leo pointed very nicely. I mean, you're always also as a company limited to what you can do, realize and tackle at once, right? And there is enough room for commercialization. There is enough room because there are so many use cases and so on what you can just extract out of it. We don't care about the actual framework itself in that sense that you have to put that as a commercial product, right? But you can just second level first, like a second derivative or so of it could be already a product, right? And containerized. So that's why, yeah, I fully agree. This is kind of how we see it and why we open source this.
Nice.
But yeah.
So unfortunately, we don't have enough time to go through the rest of the paper, which is basically the eval, which is quite cool because it's an evaluation that tries to benchmark major language models according to different aspects, like whether it can do subtasks delegation, whether it can do summarization, logic following, and associations, and so on. I leave Leo and Marius to bring us through on another session. Right now, that was a very interesting discussion about like symbolic AI. Even I learned a lot more things than I started with. I think the whole framework of using symbols and making expressions to evaluate those symbols and making these symbols very flexible and like a fuzzy equals, you can make symbols equal to one another. That's very powerful. And the fact that you can interface with multi-modality, that means symbolic AI is quite well placed in the future to integrate with leading engines. So like I think today we have come more or less to the end of today's discussion. I hope to discuss more with them in the future because we only touched on like a little bit of what we wanted to cover. Maybe I just give you all about 1 minute. Like you all have any concluding words you want to say before we end for today?
Stay tuned.
That's perfect. Yeah, I wouldn't add anything.
All right.
Stay tuned.
If not, please do follow their GitHub. Okay, so maybe you want to do a shout out to your GitHub here.
Yes, so it's ExtensityAI /SymbolicAI. And yeah, and the benchmark is ExtensityAI /benchmark. So
Yeah,
that's
I'll put the links in the video as well. So feel free to check it out. And if you have any ideas, just feel free to reach out to Leo or Marius and or even myself. I can also forward the message to them. And the main thing is we want to improve on the framework. And we want to make it more user-friendly, being able to integrate more things. And I think for that, the idea of sharing ideas, it's a big one. Yeah, I also encourage like all you like budding AI technologies out there, try to make your things open source as best as possible so that we can all learn from one another. Yeah, so yeah, keep up this spirit. I actually think that we will get somewhere. Okay, with this framework, with like even my agentic framework I'm coming up with, some hierarchical agentic framework. I actually also intending to combine some parts of it with symbolic AI. Yeah, so it will get more and more powerful. So yeah, stay tuned. All right. All right. Bye, everyone.
Bye.
Thank you. Bye.